So before we even start, let me just tell you another motivation that I had to actually do this video. You see, one of the other posts that I posted on that group was a post with this picture, and I was asking something like, "Hey, flat earthers, do you have children? And what do you tell them about the shape of the Earth? And what happens when it collides with what they are taught at school?" And some of the responses I got back, it got me a little worried, because I heard stuff like, "You know what, my son is never hearing about the globe model," or some other people said, "I hope I could I wish I wouldn't have to send my kids to school to avoid them being indoctrinated with this crazy globe Earth theory," and things like that. So it got me a little worried, because I'm thinking about that, and being like science deniers, I don't know, I think it's dangerous. I think it's bad for society in the long run, right? What kind of society are we going to build? And I thought that maybe I can do something. I mean, I can actually teach these people some simple math and geometry, and let them see for themselves that what they propose is actually mathematically impossible. So if you don't think that the basic math and geometry that you learned when you were in school was some kind of brainwashing and indoctrination, I invite you to remember those tools and come with me as I use them to make you see that the Earth cannot be flat. Okay? Okay, so before we dive into the geometry, let me do a quick introduction about myself, because that is actually relevant to the question. First, I have to show you that I don't work for NASA, or never worked for NASA or something like that, because NASA is trying to is lying to everyone that the Earth is a globe and stuff like that. So this is my resume. You can, this is link tonylampada.github.io, so you can just browse and see what I have done. Okay, my phone is ringing, just a second. So this is my resume, this is who am I, what I can do, web development, this is places I work. Okay, this is it. And you see, I'm mostly a web developer. I mean, I was mostly a web developer most of my life, but in the past few years I have worked a lot with geoprocessing. Let me type this, because maybe I'm not saying it right. Processing, right? So a lot of people don't know what this is, so let me just try to show you a little bit what geoprocessing is about. And the kind of geoprocessing that I do is related to agriculture. Okay, so yeah, so this is QGIS. This is a piece of open source software that you can use to open shapefiles, right? And I have a shapefile open here. This shapefile is some shapefile that I downloaded from the internet some day ago, probably a year ago, that has the shapes of countries in the world. Okay, and you can see that you have some coordinates right here that you can see where you are. You can zoom in and out and things like that. Now let me open another shapefile, because okay, so these are crop shapes. So where are those crop shapes? Okay, so these are crop shapes. You see, this is a shapefile that was sent from someone who works at who has farms where they grow sugarcane. That's right, they grow sugarcane in each shape like this is one unit that they control and they manage, and they grow sugarcane and they go there and harvest and things like that. So one of the jobs that I have is, hey, the problem the client has is, I want to monitor all those plantations, so maybe you can use some satellite pictures that are flying over the sky and they are taking pictures from my plantations, and you can actually see by looking at the color how green they are, if they are growing okay, and maybe you can derive some kind of intelligence from that. And this is what we do. We go to this website here called Earth Explorer. Yeah, that's right. Let me pause for a bit. Okay, it's loaded. So what this website is about is that it lets you download pictures that a bunch of satellites that are flying above our heads take of Earth, and you can download them for free. So what I do is, okay, so I have those shapes here, right? So I need to find where I can download the pictures that they take from here, and then I just go I need to find where those pictures, where in the world those pictures are being taken. So I have this other shapefile here, right? Let's make it transparent. Properties, transparency. Okay, good. So what I do is, okay, I'm going to look at this tile here. Okay, this red rectangle here is actually one picture that the satellite is going to take, and you can see that this tile here, it has this path and row attributes here, right? So they're all numbered. So this is 72, 73, 74, right? And I can use those like coordinates for all the little places that the satellites are going to photograph, to actually choose and see the pictures that I want to download. So for example, let's download some pictures from the United States. I don't know, maybe here. Yeah, so that's path 2639. Okay, so what we do is go back to this website, 2639, and we are going to ask for pictures from January this year, from up to now, and then we actually have to choose what pictures we need to download. So there are two very nice satellites that are called L7, Landsat 7 and Landsat 8. So you can look it up, right? Landsat program. You know all about the satellite program, that the Landsat satellite program that launched satellites to keep taking pictures of Earth. Okay, so I have chosen my path and row and my time period and my kinds of pictures that I need to download. Okay, so I click results. Searching. Should I pause? There it is. So we can see a bunch of scenes. So a scene is a picture of a tile on a given date, right? So this is a picture. So this is a really zoomed out picture, but I can actually download it. I just, yeah, this one, this big one. Yeah, each image is this big. So let me get a Landsat 7 because they are smaller, so we can actually open those. Okay, so let's take a look at this one. It's from June 2nd, right? Well, this is weird. It's another path and row. Did I make a mistake? Apparently I did. Search criteria 26, 39. Maybe I should put a 0 before. Really? Yeah, this sign is kind of a pain in the ass. Results. Yeah, it's kind of confusing. But the thing is, you can go here and you can download these pictures, right? And you see, each tile gets its picture taken every 16 days. And if you take a look at the dates that different tiles have their pictures taken, you will see that they are taken in a chronological order that's like this. They take a bunch of pictures that go like this, then they go back up again and like this and like this, you know, because the satellite is actually orbiting the Earth, right? So this is just one kind of evidence or maybe indication that satellites are real. Okay, now what do we do with those pictures? So we actually need to write software to take some piece of shape right here and cut with the picture that we downloaded so we can look at it. So let me just show you an example. This is a little web application that I wrote to actually look at such things. So this is one such shape, right? This white line here, this is coming from the client's shapefile, and here is a bunch of satellite pictures that shows that it's getting greener and greener, and later we will write software to actually take a look at the color of each of those pixels and try to calculate how healthy these crops are with time, right? So yeah, you see those stripes right here? That's coming from Landsat 7, which is one of the satellites. It had a technical problem a few years ago. And it's now taking pictures with a lot of black stripes like this. Anyway, so this is the kind of job I do, okay? And one of the things that we use a lot is the latitude and longitude coordinate system, because, you know, each shape has a bunch of coordinates that we need to feed into the software so that it can work. This is the kind of work I do. So I think that's relevant because well, I have to make you believe that I know what I'm talking about when I tell you that the latitude and longitude coordinate system works. So, yeah. Okay, so you can download those pictures yourself. You can verify that they match reality, okay, with the passage of time, okay, and you can expect that a new picture will be taken over your head every 16 days. Okay, so you can verify that. You can verify the order that those pictures are taken, and you can verify that those pictures date back from Landsat 7 was launched in 1999, so you have all those pictures. So yeah, I was discussing about it with a few people on that group, and they told me, no, you know, NASA are a bunch of liars, and they are flying a bunch of planes and taking those pictures. Yeah, right. Yeah, they have been doing that with amazing precision for 17 years without fail. Every 16 days they photograph the whole world and make it available for free online, and you can download it and verify. And they've been doing that with planes? I don't think so. Anyway, let's begin, right? Because this is about the geometry of the flat Earth model. Okay, so yeah, this is the flat Earth model. So this is the beginning of the class, and I'm getting worked up, so let me calm down for a bit. So this is the flat Earth model, right? The Earth is a circle, like a pizza, okay? And at the center here is North Pole, okay? And north is anywhere you are on Earth, in this pizza. North will point to the center, and south is just the other direction, okay? So Earth is a circle, and this is the flat Earth model. Day and night are actually the result of the sun circulating above Earth like this. Let me just... Okay, so this is an animation of how the sun moves, right, over the Earth. Yeah, what a beautiful animation, man. Great work. Wrong, by the way. Anyway, so yeah, so this is the where was I? Here. No, not here. The flat Earth model. Okay, so this is the flat Earth, right? The Earth is a circle, and now we are going to work some geometry, some circle related geometry, to try to figure out how things work on a circle like that. Okay, so one of the things that I want to draw the attention to is the expanding south effect. Okay, so here's the deal. You have 2 points A and B on Earth somewhere, and if you're Anna, who's at point A, south is going that direction. If you're Max, that is at point B, south is this direction, right? So if they have a compass, and the compass is always pointing north wherever you are, so if they have a compass with them and they use it to go south like this, then Max and Anna will be further apart from each other the more they walk south. Okay, so for example, this distance D2 is greater than distance D1. This is the expanding south effect. Okay, good. Let's put this in our pockets for a while. Now I want to talk about coordinate systems, right? Coordinate systems. So if we are in a circle and we want to locate a point, then usually we have two options. So we can go for a Cartesian coordinate system. So every point P has two coordinates that are related to perpendicular axes, x and y. So each point is defined by two numbers, x here and y here, and you can locate any point on a circle with a coordinate system like this one. The other option you have is use a polar coordinate system, right? So a polar coordinate system locates points by assigning first a distance from the center, r, okay, and an angle, alpha, that it makes with a given axis that you arbitrate. So each point is also defined by two numbers, but those are different numbers. This is a distance and this is an angle, and you can also find any point on this circle using these coordinate systems. Okay, next. So anyway, what coordinate system does the flat Earth use to locate points on flat Earth? Does it use the Cartesian system or the polar system? The answer is none of them. Okay, it doesn't use any of those two systems. The coordinate system that it uses to locate points on the Earth is the same that you maybe have heard, that is called the latitude and longitude system. In short, the lat-long system. Okay, so this coordinate system, it makes more sense on a globe, but since it works so well to locate points on this Earth, I mean, you can send latitude and longitude coordinates to someone else on the other side of the globe, or the flat Earth, whatever, and they will know where you are. It works to locate stuff. So how does this coordinate system works? On flat Earth anyway. First, we need to understand what is latitude. Okay, so this is the disk that represents Earth, and this middle ring here is what we call latitude 0. Okay, and latitude is a number that will measure, that will increase the more we go north, and will decrease the more we go south. Okay, and the maximum value is 90 degrees, and the minimum at North Pole, and the minimum value is minus 90 degrees. Now there are a few interesting properties about the system. First, for example, if you are anywhere in this flat Earth, let's say this black dot here, and you go east, okay, you take your compass and you start walking east according to your compass. So it will you will keep walking along this line here, and you will never have any change in your latitude value. Okay, so this is something that you can verify. You can if you get a GPS and a compass anywhere in the world, and you go east according to your compass, let's say a magnetic compass, your latitude will not change. So this is compatible with the flat Earth model. So far we are good. Okay, this is latitude. Now, what is longitude? Okay, so latitude measures the distance to the center, right? Or more accurately, the distance from this middle ring here. Okay, yeah. And longitude measures this angle alpha. Okay. Now, why don't the flat Earth people just modify the current values of, you know, latitude and longitude of points and transform it in a polar coordinate system that is centered on this point here, and then just use like trigonometry to find the coordinates for points? Well, the answer to that, it's because that is impossible. It just doesn't work. It never works. I mean, you get more and more wrong results, especially when you walk south. Okay, but anyway, if you use latitude and longitude, you can find stuff on this Earth. And actually, I'm not saying what longitude is. So longitude is this angle here, right? So they elected, I mean, they people who decided, they elected one line here that passes somewhere, cuts France and cuts Africa, and they called, well, this is going to be longitude 0, okay? And they measure this angle here, and this angle is the longitude. So longitude varies from minus 180 degrees to plus 180 degrees. Okay, and also another property of longitude is that if you are anywhere on this Earth and you are, for example, in this dot here, if you go north or if you go south, your longitude will not change. So this is something you can try as well anywhere in the world, and it is going to work every time. Okay? Okay, now there's also another important relationship between longitude and time, right? And this is actually easy to understand, because the longitude is the size of this angle right here, right? And the sun, it revolves around above the Earth like this, and it takes a whole day to do it. So it takes a whole day to do a 360 degrees in 24 hours. So the relationship is that for every 30 degrees you get a 1 hour difference from city A to city B. Okay, so if I have 2 points right here, A and B, with those latitudes and longitudes, and then you get this angle here with the North Pole on the center. One way you can measure this angle here, you just subtract the longitudes from A and B. Now, another way you can calculate this angle is you can actually use a sundial. A sundial is like a shadow clock or a shadow watch. Let me get a picture of it. Hey, look, how cool is that? They have a 3D printed sundial that can actually show like a digital display with the time. It's awesome. Anyway, you can actually use a sundial if you put a sundial on city A and city B, and then if you measure how long does it take for them to tell the same time, then you can use this relation to measure this angle here. So you can measure this angle by actually looking at longitudes, or you can do the hard work yourself and use sundials to verify this. Okay, we are getting closer. Okay, so far this is what we know. One, the Earth is flat. Two, a difference in longitude is a measure of a time difference, right? I have two cities with different longitudes. You subtract the longitudes, then you get the angle, and that is also a measure for the time difference between the cities. Like, okay, this city is 1 hour and 20 minutes ahead of mine. Right? And then we get time zones to truncate those values to the next half hour or full hour, but that's another issue. 3, walking on the south-north line will not change your longitude, and also walking east-west will not change your latitude. Okay, now I want to talk to you about an experiment that you can actually do to observe, to verify the expanding south effect. Okay, so how do you do it? Okay, so how can you observe the expanding south effect in real life? So let's say you and another friend, Anna and Max, they decide to unite on point A. Okay, and then the next thing is they say, okay, Anna is going to walk a great distance, let's say 1,000 kilometers to east, right? And because east is a changing direction, then what she will do if she keeps looking at her compass and keep her east is that she will do a curve like this without even noticing, because you know it's a very slow curve distributed over a great distance. But if she can get her compass to work right, to work precisely, then she can be on this line and reach point B, which is 1,000 kilometers over this arc from A. Meanwhile, so this is moment 1, and then on moment 2, Anna is at point B. Meanwhile, Max is going to use his compass and walk south another 1,000 kilometers. Okay, so he can also look at the compass, and then he will reach point C. Okay, so at moment 2, both Anna and Max walked 1,000 kilometers each, and then they are at points B and C. Now Anna is going to move south another 1,000 kilometers and reach point D. Okay, and here is the grand finale of the experiment, where Max will go east until he reaches Anna on moment 4, and then Max will measure this distance, and he will verify that this distance is greater than this distance, meaning CD has a longer length than AB. Okay, now we need those distances to be of this kind of order of magnitude. This will not work for small distances like 10 kilometers or even 100 kilometers. because the difference between what you will measure between CD and AB will not be very significant, so it won't tell you very much. I mean, you probably will be thinking, okay, maybe I did something wrong, maybe I didn't keep my compass right, okay? But this is something you can do. Of course, you don't have to walk, you may drive or fly a drone, or I don't know. But this is an experiment that is measurable, it is repeatable, it is observable, and it is testable. Or isn't it? Okay, and also I want to stop for a minute and talk about measuring distances. So let's think for a minute, how competent are we human beings in measuring distances? I mean, I would say we're pretty good at it, right? We have to build roads, we have to build railroads, right? We need to know how much rail we need to buy to build a railroad. How can we do that? Only if we know how long is it, how, yeah, we need to build power lines, okay? So we're very good at measuring things. And if you talk to people who need to measure things on this world, you will learn that they rely a lot on the lat-long coordinate system. I'll give you an example. So, for example, one day we received a shapefile from a client that was using a projection that wasn't okay for the position on the map. What this means is a projection is a few mathematical transformations that you can do to coordinates, to say latitude and longitude coordinates, to transform them into metric coordinates back and forth, right? Because sometimes you can't use latitude and longitude coordinates because, I don't know, maybe you're trying to measure the area of something, right? And so you can't say, hey, this area is 0.25 degrees squared. No one knows what that is. So you have to convert them between metrics and latitude, lat-long coordinates back and forth, and for that you use projection. And because the Earth is actually a globe, you see, you need different projections for different places in the world, right? So, yeah, let me. Okay, so if you're a flat earther, I really hope you don't go out running, screaming because I just opened Google Earth, but I just want to make a point. So you have lat-long coordinates, and let's say you use a projection where you put an axis here and another here. So I'm just using those white lines because they seem to be perpendicular. And you start, you decide that this point right here is the origin of your whole metric coordinate system for the globe. So what happens is, if you use these coordinate systems right here, it will work just fine. But if you try to generalize that and start to use it here, you see, because of the curve, I'm sorry, the positions predicted by these coordinate systems will be somehow a little bit off. Okay, so one day we received a shapefile from a client that was using the wrong prediction, and all those shapes, they were a little bit to the right, like this, something like that. Okay, and we ran all those simulations and stuff, and what happened, let me tell you what happened. Yeah, that's a good one. Nope. You see, let me try to zoom up. Yeah, sorry, man. Okay, you can see here that are some lines between some more green areas, right? So this is where they plant stuff, and these more brown places right here is where they drive the trucks to actually harvest and take away all the stuff that they have planted. So if you have a shape like this that is shifted a little bit, I don't know, maybe 30 meters, 60 meters, then what you get is that the amount of green you are going to see with your software when you just try to process this piece of image will be contaminated by some amount of brown, and then when you try to measure the vegetation indexes, then you will get worse results. So there was one day when we realized we were getting very bad results, and then we started to trace back where the error was, and the problem was on the projection that was used for the shapefile that we received. So we had to fix that, right? What I'm trying to say is, if people uses a coordinate system that misses even by a tiny amount, people notice. People like me who does geoprocessing, people who I don't know, need to build railroads. There are all kinds of people who need the ability to tell distances, and they do that by using a coordinate system. And the most reliable coordinate system that you can use in the world to locate stuff is the lat-long coordinate system. Okay? Okay, good. So let's go back to the expanding south experiment. So you can do this experiment yourself. Of course, it's a little bit expensive, but it's possible to. It can be done. I mean, for something as important as determining the shape of the Earth, it's obviously worth the effort, right? Obviously. Anyway, let's go back to what we saw on our first whiteboard picture. Let's see. The expanding south effect. Define the expanding south effect. Now, where on Earth should we be able to observe the expanding south effect? Everywhere, right? And well, we can actually observe them a lot. Observe the expanding south effect a lot. Let me maybe find some place here where I can run this experiment. Okay, let me put a place mark. I don't know, maybe here, 39. 40 degrees, yeah, that's fine. Okay. So I'm using Google Earth here. You can probably argue, well, you can't use Google Earth, I can't trust it. But we'll talk about that in a minute. So this is point A. Okay, so point A is at latitude 40 and longitude 104, 40, 25. 40, 25, 104, okay. So, yeah. Maybe 94, okay. What was it again? Damn. Let me, no, I'm not pause this because people will tell I cheated. Oh, yeah. 425 minutes. No, not 440. Sorry. 25 minutes. Okay, good. This is A and B. Right? It's NIMAX. And they have the same latitude, give or take, right? 40, 25, 40, 24, it's close enough. Okay, now how far apart are they? Let me be your ruler, ruler. How far apart are they? Kilometers. Ooh. Let's start from B. It's 700 kilometers. Okay, let's write that down. AB 699.62. Okay. Again, people use these coordinate systems to measure things, and they get job done with it. So you can most likely trust this. But let me write this down, because you know, it might not be true, right? I'm sure some of you will say that this might not be true. Google Earth can be used to measure distances. And I'm going to paint this red because I don't know if this is true. Okay? Fine. Now, let's go back to our little experiment and actually find a point just below A. Now A, damn it, is at longitude 104 and 6. So we are going to drop down something, some, I don't know, some distance that is close to this one, right? That looks more or less like this one, and put it below A. And this will be point C, 104 and 6. Okay. Yeah, it's close enough. Close enough. So this is point C, right? Okay, now point D will need to have the same latitude as C, which is this one. Let me write it down because I have a really bad memory. And the same longitude as point B. Sorry. I'm going to have to put it again. Okay. 104 and 6. Sorry about that, guys. 104 and 6. Oh, no. Yeah, that's close enough. And this is C. C. Okay. Not cancel. Right. Now the next point, we'll have latitude. This one. Okay. And longitude. This one here. Long. Okay. $35, $16. Right? 95, 6, 35, 16, 95, 52. And 95, 52. I can actually type here, right? Man, I'm so dumb. Yeah, like this. Does that work? I don't know, I don't use this a lot. Okay, so this is point D. So I actually don't care about the distances A, C, and B, D. I just care that I can see that this distance here is greater than 699 kilometers. And it is. Yay! Yes! Yes, this is proof that the Earth is flat. Not quite. But it is compatible. Yes. And you can probably tell, well, you cannot do that, man. Those coordinates, they are provided by NASA. Okay, you can do the experiment on land, and you don't need to do it on Google Earth. But if you wanted to do on Google Earth, then you also have to trust that Google Earth's compass is right. That's because you need to be able to tell that the line connecting C and A are actually pointing north, right? So this compass here, you have to trust it, because if those points, they don't have any difference in longitude, then this compass should be pointing north. Okay, now this is something that you can verify. This is something that you can verify. Can I trust Google Earth's compass? Oh, that's easy. You buy a magnetic compass, you go to a few places in Earth here and there, and you look at your compass, and then you look at the direction that Google Earth's compass is pointing, right? You can, well, actually, to be completely rigorous, you need to actually trust that Google Earth's compass behaves consistently. And what I mean by this is that you should be able to verify that this also happens in Google Earth. These two rules here, they should happen on Google Earth. So you have to trust these and these and these. Okay, so those are like rotten apples, right? So we don't know if those are true, but if they are, we can actually run the experiment here on Google Earth. Okay, now can you tell where in the world does this experiment works? Where we'll get distances that are consistent with this rule, with the expanding self effect? Well, the answer would be on the northern hemisphere, or the inner ring, whatever you like. Okay? It certainly does not work here. Now these are dangerous lands for a flat earther. I mean, according to flat earth geometry, Australia cannot exist. So I'm not going to do this whole experimenting on Google Earth again, but you can do it yourself. It's very easy. You just saw how I did it, and it's also possible that you can do it on land. Now, if you can get the expanding self effect to work only once in the southern hemisphere, here on Africa, some in Australia, here on Africa, and here on South America, if you can get it to do only once, I'll give my card to you. I don't know, right? It won't work. What happens is that as you move south, those distances, they are brought closer together. So the number of places on Earth on the let me open this again, because on this outer ring where you can get the expanding self effect to work, the number of places that you can get it to work on this Earth is 0. It doesn't. As you go south, things are brought closer together everywhere. And you can confirm that by using software, or you can confirm it on land. You will never get this expanding self effect to work on the southern hemisphere or the outer ring or whatever. So if you are like a globe head, right, when they ask you where's the curvature, well, where's the expanding south? Where is it? Because I can't see it. I mean, there are people who says they saw the curvature, right? There isn't anyone that says they saw the expanding self effect on the outer ring or the southern hemisphere. because it's just not possible. And if you find anywhere on Earth where that happens, then you can just tell people what the coordinates are, and they can repeat it, right? They can do it again. Yeah, because this is a measurable, repeatable, observable, and testable experiment. Okay? Yeah. So, not gonna happen. Not on this Earth. Okay? It should happen in a flat Earth. Right? Yeah. Let us do another experiment on Australia. Just to close this video because it's getting way too big. Okay, so before we start the experiment on Australia, there's actually another piece of math that we have to look into. Okay, so this is simple. You see, we are trying to measure the size of this arc from A to B, given that we know the distance from this radius OA and this angle alpha, right? So there is a whole circle around O like this, and its length is 2 times pi times d, which is the diameter times pi, and we only want a fraction of that, so that fraction is actually this angle alpha over 360. And then we can simplify this formula by slashing this 2 with this 360, and then the length will be pi times d times alpha over 180. Okay? And also, if we actually want to know the value of d, right? If we have the length L and the angle alpha, then d will be 180 times pi times, sorry, not pi, times L over alpha times pi, right? I'm looking at this equation right here, and I'm just isolating this d guy. So I'm multiplying this 180 by L, right? And then I'm dividing the result. I'm actually moving pi and alpha below, so they will be below this slash, like this. Okay? Yeah, so we are going to use this to actually calculate some, I don't know, some approximation on the size of the flat Earth. Okay, so let's find the equator. Crashed! My Google Earth has crashed. Okay, so in this next little experiment, we actually want to calculate how big would be the flat Earth. Okay, so I'm zoomed in this is not Google Earth anymore, because here I can get you see those coordinates here, they are better to make calculations with them, because Google Earth will tell me latitude and longitude with minutes and seconds, and so that's not good. Anyway, we are very zoomed in in a place, I don't know, any place near the equator. I really don't know where this is. I just zoomed in the equator. You can tell that I'm near the equator because you see no significant increase of this is actually longitude and latitude, yeah. So you don't see a significant increase of latitude as I go up and down here, north and south. So this is near the equator, right? And then this tool here, which is called QGIS, it can also calculate. It has a ruler tool as well. Where is it? Here. So we can take, I don't know, 2 points here and measure this distance. Okay, and this is an arc like this one, right? Because those 2 points are on the equator and the North Pole is way up above, and there's an angle between them. Okay, anyway, I don't know about the angle yet, but the distance should be 4.064 kilometers. So that's so let's start over. Length equals 4064 meters. So this is the length of this arc here. Okay, also we have those two extremes with different longitudes, so we can subtract the longitudes and get the alpha angle right here. Okay, good, let's do that. So the first is this 56, hang on, 56.54261, 54261. And the second, let's get to the other extreme, 56.5061. So the angle alpha in this picture here is actually this difference. Okay, so yeah, if I want to subtract them, then I switch the signal here. Let me open my calculator and I will say alpha equals this, and then L equals 464 meters. Okay, now okay, this is a programming language, so I can use an asterisk to do multiplications. So this is D, like this. So what is D? Okay, we had a signal difference because of this angle difference, but it doesn't matter. So we can just forget about the signal. So B over 1000. So this is the distance from those points to this origin here. So there's something around 6,400 kilometers, right? And what is this distance on flat Earth? Well, flat, blah, 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 blah. No, not good, not good. it's the distance between the center and a few points that I found with 0 latitude, right? So it's this distance here. So the radius is actually twice that big. Okay, so this is flat Earth. The middle ring should be somewhere 6,390 kilometers from the center, and then because this is the middle ring, then you get another 6,000 and almost 400 kilometers to the icy ring. Okay, let's just remember that. Now, you know what? I'm gonna draw it. Not right now. Anyway, here we go to Google Earth again, and we're going to go here. Yeah, Perth. Okay, you know what? Maybe I can just use Google. Perth, latitude and longitude. Okay, this is Perth, Australia, right? No problem with this. And there is another city that is called Sydney. It's here. Okay, good. Now, what is the latitude difference between those two? Right? It's this minus this. Okay. Okay, so it's 35 degrees. So those two cities, they should be they should have something around 1 hour of this difference between them. Let's see if that is the case. Okay, this is Sydney. What time is it? In Perth. There's actually a 2-hour difference, but that's kind of in the extreme of the what should be allowed given the time zone difference, but that is still okay. Anyway, we can probably trust that the angular distance between Perth and Sydney is something around 35 degrees, right? Even in a flat Earth. Let's take a look at yeah, this is the one that keeps popping up. Oh yeah, this is a really great example. You see this map here? You see Australia here? Okay, so Perth should be here, and Sydney should be here, right? So each line, each white line on this map is 30 degrees, okay? Because this is 90, and then you get 1, 2, 3, 4, 5, 6. No, sorry, not 30. It's 15 degrees. So did I say this map was wrong? No, I was wrong. Sorry. Each 2 slices of this pizza is 30 degrees. So the length of Australia here is somewhat around 30 degrees, a little bit more. That's okay. Also, let's see if we can. So we can probably trust. We can probably trust that. Where is it? That there is a little bigger than 1 hour difference as measured by sundials from the extremes on this continent, right? Okay. Yeah. How far apart they are? Between Perth and hey. No, I don't want directions. Hey, okay. So this is car. Sydney and Perth. Well, let's see what Google Earth says. In a straight line, anyway. Where is Sydney? Where is Sydney? Sydney. Nope. Sydney. Ah, come on. Okay, here it is. Perth should be somewhere here on the other side. And that's okay. We don't actually need to get too precise, okay? Because the results, maybe Perth is around here. And Sydney is over there, so it's 37.95. Okay, 37.95. Sydney to Perth, kilometers, and it's also 35 degrees. Again, no need to be precise about this. Okay, so they have around the same latitude, so I can roughly say that there is an arc like this one between Perth and Sydney, and I know this length and I know this angle, so I can calculate this distance. Let's try to find out what it is. So we already have alpha, and L is 3,700 kilometers, and then D, which will be in kilometers this time. It's the same formula, right? Yeah, indentation. Okay. Well, okay. So let's draw this. Okay, so we damn it. First, let's recapitulate. Let's remember what we just did. We found some random points very close to each other on the middle ring, on the equator, right? And we used the angle difference and the distance between them to actually calculate how their distance to the North Pole, right? And the result was this. Okay. We also used the same formula by and took two different points here and here on different sides of Australia, right? And we used this distance, this straight line distance, but we shouldn't have used an arc, but it doesn't, we don't really need to get too precise about it, because the result that we get is that the distance from the North Pole to the S arc here is 6,150 kilometers. So where does that put Australia? Australia should be almost entirely inside the middle ring. I mean, we will probably sink those islands here, right? Yeah. Australia can't be. Can't be. Do you know what that is? Why that is? Because you see, remember the self-expanding effect, right? So those white lines here, they will keep expanding until they reach this red line, which is the equator. Okay? Then they will start to shrink. Those white lines, they will start to get closer together again, because there is no self-expanding effect outside this ring. It can't be observed, and I dare you to. You won't. Okay? Then, if you could bend those white lines here closer together again, then Australia would make sense. Right? It would. But it doesn't. And this is, I don't know, maybe you've heard this story where people say, well, we can't really build an accurate map of the flat Earth, you know, because it would be too expensive to visit a lot of places. I don't know what, I mean, they come up with an excuse that it's too expensive. Yeah, you can't bribe Australia into moving up, right? Geometry is not a whore that you can pay it to do whatever you want. It just isn't. So this map will never work as long as we have a latitude and longitude coordinate systems that works better and works perfectly everywhere. Everywhere. It works everywhere. Right? I told you, I do a lot of geoprocessing here, and I need in a 30 or 60 meters error, it's very hard to miss, right? So the very fact that there can be a latitude and longitude system, coordinate system that works on this world, makes it impossible for it to be flat. It cannot, because, you know, those white lines, they would all have to start bender closer together again from this red circle and outside. Right? Now, okay, so where was I? So the Earth, it cannot be flat, because if it was, we would see the self-expansion effect everywhere, right? Again, if you go south, you get further apart, right? But what happens in reality, everywhere below this red line here is the opposite. They start to get closer together, and this is observable, repeatable, and etc., etc., etc. So this shape cannot be, just cannot be, unless you fold it, right? Unless you fold it. Maybe we could bend this paper here, and I don't know, maybe we could join this white circle behind on the other side. Then these lines would get closer together again, right? So this proves that the Earth cannot be flat, and it also shows that a globe doesn't have the same problems that we bumped into. Okay, so as a final message, I just want to thank you for watching this video. This is probably longer than it should have been, but I think it's worth being thorough. And I know that many flat earthers that know some geometry and can follow this, they will be upset, and they will be I don't know, but hey, this is just the shape of the world. You know, the world doesn't have to end because of it. I mean, if you find out that you were wrong, what's the problem with that? It's okay to change your mind given new evidence. So this video is some new evidence, and evidence that you can. This is full of evidence that you can confirm for yourself. Okay, but if you still want to I don't know, debunk the globe, here's what you should do. Let me help you with that. You can try to find one example where those things are not true, because you know those softwares, those pieces of software, they are like a proxy to the latitude and longitude coordinate system. So if you find an error here, then you're onto something, right? You're onto there's something wrong about the lat-long system, and maybe the Earth can go back to being flat again. But anyway, this, I hope this does not start a crusade to, I don't know, maybe find somewhere on Earth where, on Google Maps, where the compass is not pointing north. Yeah, I don't recommend that, because you probably won't. Anyway, so yeah, that's it. And if you find any mistake with the reasoning that I presented, please let me know in the comments, and I will be happy to examine it. and I will not have a problem changing my mind, given new evidence. And you can proceed believing whatever you want to believe, even about the shape of the earth. I don't want to challenge anyone's religious beliefs or anything like that. I just think that it's not healthy for society if we have a growing number of individuals that keep denying science. Science is a good thing, is what enabled progress. And of course, there are new problems that come up too, but the solution can't be not sending kids to school or things like that. Can't be. It will build a worse world if we do that. So please think about it. Thank you very much.